Muchas gracias por la invitación y estoy muy agradecido a la CEA por darme este premio. Estoy muy honrado de poder estar aquí hoy y presentar mi trabajo, mi ciencia. Y también quería agradecer mucho a mis directores de tesis, a Héctor y Licia. Héctor también está aquí. Y bueno, voy a seguir en inglés para que vaya más rápido. So the title of my thesis is From the Precision Era Towards the Accuracy Era of Cosmology with DESI. And throughout this talk, I will take this title as a guideline and kind of go through the different parts that are encoded in that title. So first, let's start with DESI. So the Dark Energy Spectroscopic Instrument is located at the 4-meter Mayal telescope in Arizona. And it's actually located in a reserve of the Tohono-O'odham Nation, and we have the privilege that we can do science on that reserve with the allowance of the people. And so in the past 3 years, I've been part of the Education and Public Outreach Committee of DESI. I co-led that committee together with Claire Laman, who's on that picture. And we want to engage more with the local community there. Here you see a picture of a rodeo parade in Sales where there was some astronomy-related themes in this parade with the Tohono-O'odham Nation. And Claire drew this wonderful comic figure, the DESI ambassador, Baoban. And I've written a blog article on how the name Baoban was chosen together with the community who voted on that. If you are interested in that, have a read. I think it's really interesting. So I also leave it to Baoban to explain what makes DESI so special. The thing that makes a difference is this focal plane, which consists of 5,000 individually controlled robots that point fibers to individual galaxies, and so you can measure 5,000 spectra simultaneously. So this is a view of that focal plane, so they can really position themselves, and you can, as you scan the sky, you can point them towards the galaxies you want to measure the spectra of. So that's exposure takes like 20 minutes. So each 20 minutes we get 5,000 spectra. We do this for 5 years. This is the progress that has been done in the first year of observations. You see all these tiles that we get on the sphere on 14,000 square degrees. So let's zoom into that part, which is the densest part we have observed so far, and talk about how we can do cosmology with DESI. So probably many of you have seen this announcement from April the 4th. The first results from DESI make the most precise measurement of our expanding universe. The New York Times even titled that there's a tantalizing hint that astronomy's got dark energy all wrong. So I will not talk about this here, but if you're interested, there are 3 DESI talks by Violetta, Hector, and Nicola in the parallel session on cosmology this afternoon. I would just like to talk about how do we do this measurement? How can we actually extract the expansion history? How do we extract cosmology from this 3-dimensional map of galaxies? So one thing that we measure, one imprint, is the so-called binary acoustic oscillations. So in the CMB, in the cosmic microwave background, there's the scale imprinted, the so-called sound horizon, RD, which is like on average, the distance between 2 hotspots in the CMB. It's like the most abundant correlation in the CMB, which has to do with the fact that sound waves could travel from the Big Bang until the time the CMB was emitted. They traveled that distance. And this scale is imprinted later on, even in the distribution of galaxies. So we can measure at different redshift bins, so these are the different types of galaxies DESI is measuring at different distances and redshifts, and we can measure the distance perpendicular to us and parallel to us, to the line of sight. And we know the distance must be the same everywhere, so we can really use it as a standard ruler to trace the expansion history of the universe. And another effect we get from this data set is encoded in the so-called redshift space distortions. So if you have a galaxy like the white galaxy there, that's the real position. But if it has a velocity, the component that is along the line of sight actually makes it look as if it would be at a different position, because we see the velocity from the Hubble flow superimposed by the proper velocity, so the galaxy appears to be at this gray position. And that distorts, induces an anisotropy in our signal, which is along the line of sight. So how do we measure, how do we get this signal? So what we do is pair counts. We just count how many pairs of galaxies exist at a given distance. So it's like throwing sticks with different distances at different angles and just counting how many pairs of galaxies have exactly that separation and angle. Okay? Then we create like a histogram. We call it the two-point correlation function, xi, which depends on the distance and the angle with respect to the line of sight. We can do a Legendre transform to get the multiple expansion of that. We call it the correlation function multipoles. And we measured this for DESI, and this is how it looks like at different redshift bins. So you see in the upper panel is the monopole, so it's the isotropic component of the BO signal, and you see it has this bump, this beautiful bump, which indicates there's an excess of clustering of pairs that have that distance, and that we can use as a standard ruler. And we also see it in the quadrupole, so it also has a peak, but also importantly, so I call it the horizontal information. So the scale at which we measure this peak is like, we fit like a horizontal template to that, scaling it with these parameters alpha. And we have also the vertical information, which gives you the strength of the anisotropy, which is induced by the redshift space distortion. So the quadrupole, actually, normally if we wouldn't have redshift space distortion, there would be no velocities of the galaxies, we wouldn't have measured any quadrupole, it would be zero. But the fact that it's non-zero really tells us, yes, there are velocities, and the size, like how fast these galaxies are, depends on the strength of the gravity and how much have they clustered. All right, so that's how the cosmology we do with DESI. And now I'm talking about this idea of precision versus accuracy. I think you're all well aware the difference between both. In Spanish, I think it's precisión y exactitud. So you can be, if you throw darts into the sky, you can be accurate and precise, okay? You can be accurate but not precise, so you have like a large statistical error. You can be neither accurate nor precise, or you can be very precise but not accurate at all. You are just off. But in the end, we always want to be accurate and precise. Interestingly, in cosmology, there's this term, the precision era of cosmology, which was heralded with the CMB, or I don't know, it's used, it's very commonly used, that phrase, precision era. And I searched on NASA how often this term is used. And you see, it appears hundreds-fold every year in cosmology papers. Whereas if you look for accuracy era, there are only very rare papers that mention accuracy at all. And I was wondering, why is this the case? And I think it's because claiming precision in cosmology is relatively easy. You can say, I have a small statistical error, I have tight constraints, I'm precise. Whereas claiming accuracy is hard, if not even impossible, because you have to say, I accounted for all the systematics, but there might always be unknown systematics, so you could never know with certainty that you are actually accurate. And it's actually unscientific if you say, yeah, that's accurate. We don't know until, you know. So actually the most important word in that title is probably towards, because it's always a process you go towards. You cannot claim ever 100% accuracy, right? So let me talk now about the ingredients in my thesis that help to go towards that direction. So the first idea is the idea of blinding. You probably have heard of this. So if you do a blind experiment, it means you analyze the data without knowing the implications of the results. So you know it from psychology, medical studies, blind studies where you don't have the key to analyze who got the real medication, who got the placebo. But how do we do it in cosmology? So first of all, of course, I don't mean blinded, like we don't know what kind of experiment we are doing, so it's not that type of blinding I'm talking about. And actually, it's more accurate to say that in the universe, in cosmology, we don't do any experiments, so it's more like the universe throwing light darts at us, and we just measure where they arrive, right? So what we suggested was to blind the galaxy catalog itself. So we impose an additional shift on the galaxies along the line of sight, and then which is particularly targeted to blind this BAO and RSD signal, which by changing expansion history and having a density-dependent shift that mimics the different velocity of galaxies. And so we pitched this in the DESI meeting in Berkeley in July 2019. I think everyone thought that we were crazy by that time, because why would you blind the catalog? But we presented this in a paper the year after, where we validated it on the available data set and on MOX. And we outlined like a plan. How can you, in such a big collaboration, how can you implement this catalog level blinding and have the team analyze only the blinded catalog, and what are the feedback loops until you can converge on really unblinding the measurement and saying, yeah, now we are confident with how we treated our systematic uncertainties, and we settle on that fiducial choice before you have seen the actual result. I think that's very important to avoid confirmation bias. And so this, from then on, it has been implemented, and we have implemented it within DESI. We have also published a paper this year led by Brieden and Juan Mena Fernandez on how it's actually on validating on the DESI models that match the actual DESI geometry of year one. And there's even more papers that have been coming. So there's an extension of the blinding scheme with systematic weights, also at the catalog level, to blind for the so-called primordial non-Gaussianity signal. And there's a paper upcoming in the next few days by my fellow PhD student Sergi, who has tested the blinding scheme even on the bispectrum, which is not the 2-point correlation function, but the 3-point correlation function. So that's really cool and nice to see that this is going forward. So the second ingredient of my thesis is the so-called shape-fit compression. So if you remember, I talked about the horizontal and vertical scaling of these correlation functions. And what we added in this paper, part of my thesis, was the shape or the slope. So we added kind of the diagonal information as well. And we showed that by adding that information, you get actually all the information mostly that you need in order to constrain cosmology. And it gives an additional parameter. We had the 2 alphas, the growth rate, and M. So now we have 4 parameters that we can compress everything, the data into, and that really encodes all the cosmological information almost that we need. And so if you ask why do I call it compression, it's kind of, so if you think about it, right, we started from 2 billion galaxies, photometric galaxies that we could target, and we only select 50 million spectra, so we throw away a lot of these galaxies. And then we do the summary statistics, which are roughly 100 data points per redshift bin, and we compress it into these 3 to 4 numbers per redshift bin that encode the cosmology. So it's a huge compression if you think about it. I was thinking it's kind of analogy to spending 4 years of my PhD, most of it is wasted time, into 280 pages of thesis, which then leads to 1 hour defense and then a 50-minute talk at SEA, so it's also a huge compression. And so this is the main result. So this from the data, the predecessor experiment of the EBOS, we applied this method and measured these 4 parameters. Here we show their correlation and how they look like in different redshift bins and how they compare to the cosmological model, the lambda CM model, and it looks quite nice. And another important thing is that with this new parameter, we are actually able to isolate some systematic uncertainties, which I encode with all kind of observational systematics. I don't have time to go through all of them, but you can basically look at what happens if we exclude this treatment of the observational systematics. And we showed in one publication that this is mostly absorbed into that new shape parameter. So you can constrain cosmology from that shape, but you also have to be cautious that the shape is mostly affected by systematics, whereas the BAO and RSD parameters are more robust. And I think that's also a very important lesson learned from that project, that you can be precise, but you have to make sure that you are robust and and look at the accuracy as well. And that's why shapefit is also used for DESI. It's been used to validate some ELG spectroscopic systematics for year one, and also used to validate the fiber assignment of the DESI fibers. So to conclude, my thesis consists of two parts, basically. One was the blinding, which is important to remove confirmation bias as a source of potential systematic uncertainty, and shapefit, which is important to balance between maximizing precision on one hand, but also maintaining robustness and making really checks. How am I affected by observational systematics, actually? And I think both works deliver a puzzle piece towards entering the accuracy era with DESI, and as you have seen, it's in used and an integral part of one analysis. And the final thing I would like to mention is there was actually an unblinding shapefit event 1 month ago. So that was like the culmination of all my thesis work, because like you unblind the shapefit measurements. So that was really nice. Unfortunately,